Oh, someone is asking about exam 3 on Pearson. I should have changed the date, so you don't have to do it by the end of today. That's fine. Okay, so Lagrange multipliers. So this is page 1002. And let's look at number, I don't know, try number 13. So we have a function f of x, y equals e to the x times y. And we have a constraint, which is x squared plus xy plus y squared equals 9, which is the same as x squared plus xy plus y squared minus 9 equals 0. So we want to maximize this function subject to the constraint that g of xy is equal to 0. So we look for a points x, y, and numbers lambda. The lambdas are what are called the Lagrange multipliers, such that the gradient of f at x, y is lambda times the gradient of g at x, y, right? That's the condition for finding a local maximum or a local minimum of the function. So the gradient of f at xy, if we differentiate f with respect to x, we get y times e to the xy. And if we differentiate f with respect to y, we get x e to the xy. And the gradient of g at xy, if we differentiate g with respect to x, we get 2x plus y. And if we differentiate g with respect to y, we get x plus 2y. So to say that the gradient of f is lambda times the gradient of g means we want to find the numbers lambda such that y e to the xy, x e to the xy equals lambda times 2x plus y, x plus 2y, or 2x plus y lambda, comma, x plus 2y lambda. So we have to satisfy these equations that y e to the xy is 2x plus y times lambda, and x e to the xy is x plus 2y lambda. And the trick that we've used several times is to subtract one of these two equations from the other. So if I take the first equation minus the second, I get y minus x times e to the xy. And when I subtract this from this, I get x minus y times lambda, or if you like, minus y minus x times lambda. So one possibility is x equals y and any lambda. If x is different from y, you can cancel, and you get e to the xy equals minus lambda. So so let's see what happens in those cases. So, of course, if e to the xy equals minus lambda, in that case, because that function f of xy is e to the xy, this just means f is constant. F of xy is equal to minus lambda. And if you take the function which is the constant function minus lambda, which is lambda everywhere, so lambda on this, that's one value the function f of xy can take. If x equals y, f of xy is equal to e to the x squared, And we want to maximize that subject to this constraint. If x equals y, you get x squared, another x squared, another x squared. You get 3x squared equals 9, x squared equals 3. X, in that case, x is equal to plus or minus the square root of 3, and f of x, y is e cubed. So you get the extreme values of the function f equal to, let's should say one other thing. So if x equals y, the function that takes the value e cubed when x is plus or minus the square root of 3. What about this lambda? So what can we say about lambda? So if e to the xy is minus lambda, let me just squeeze this in over here. E to the xy equals minus lambda means y e to the xy is minus lambda y is 2x plus y times lambda. If lambda is different from 0 and you cancel it, you get minus y equals 2x plus y, or 2x equals minus 2y, x equals minus y. So when x is minus y, can't squeeze it all into this one page, so let me just start again, and just to make it a little bit neater. I have the function f of xy equal e to the xy, and we want to find the local extreme values subject to the constraint that g of xy, which is x squared plus xy plus y squared, is identically equal to 9. So when we solve gradient of f equals lambda times the gradient of g, what we get is that either x equals y or e to the xy is minus lambda. If e to the xy is minus lambda, we had the equation y e to the xy is lambda 2x plus y, or minus lambda y is lambda 2x plus y. Lambda is not 0 because the exponential function is never 0. In fact, lambda is always positive. But this says that minus y equals 2x plus y, 2x equals minus 2y, or x equals minus y. So the only possible extreme values of this function could occur when x equals plus or minus y. When x equals plus y, g of xx is 3x squared equals 9. So x squared equals 3. So x equals y equals plus or minus 3. And in that case, the value of the function f of xy is equal to e cubed. So when x and y are equal to each other plus or minus 3, f of xy is e cubed. If x is equal to minus y, x squared plus xy plus y squared is x squared minus x squared plus x squared is x squared equals 9. In that case, x is equal to plus or minus 3, which is minus y. And in that case, e to the xy is e to the 3 times minus 3, 3 times minus 9. So at the points 3 minus 3 and minus 3 plus 3, the value of the function is e to the minus 9. At the points root 3, and minus root 3, the value of the function is e cubed. So this is the maximum value of the function on that constraint, which is some ellipse, and this is the minimum value. Does that make any sense? I mean, there's always a lot of work solving a problem using Lagrange multipliers. It's not just enough to know what to do. To actually do it involves usually a fair amount of calculation. Okay, so in calculus, there are two fundamental operations, which are differentiation and integration. And we've been looking at derivatives of functions of several variables. You have the partial derivatives, the directional derivatives. They combine into something called the gradient. And now I want to consider integration. So we have some function z equals f of x, y. So you can think of that as over some region R in the plane, you have the surface. And we want to create a theory of the integral. Let's call it a double integral, because f is a function of two variables over this region R. We want to make sense of this in some way. And we can begin by recalling how we did an integral for a function of one variable and how we motivated it. So if we have y equals f of x, we had, this is the graph of the function. It's a curve in the plane. And if you ask the question, let's say this is a non-negative function, what is the area under the curve from x equal a to x equal b? That means bounded below by the x-axis and above by this curve. And this area is equal to the integral from a to b of f of x dx. So in a similar way, if we're looking at a function of two variables, we have the surface. Let's say the function is non-negative, so the surface lies above the xy plane. Instead of looking for the area, we can look or ask about the volume. What is the volume under the surface going to be? So let's start with the simplest case. And the simplest case is where R is a rectangle in the XY plane. So what that means for us is you might have X goes from A to B, Y goes from C to D. So this rectangle would be X between A and B. So we're looking at values. This is X equal A, this is X equal B. So in this strip, but also Y between C and D. So Y is greater than or equal to C and less than or equal to D. And the set of points that satisfy both inequalities is this rectangle. So this is the rectangle R. And you can imagine where, so here I'm now drawing X, Y, Z. So what a rectangle looks like when I draw in a perspective like this is my rectangle R. This is A and B, C and D. And sitting over this rectangle in the XY plane is some surface. And we can say we want to find the volume above the XY plane and below the surface over this rectangle R. Now think for a second, if you can remember back to Calc 1 and Calc 2, how'd you find the area under this curve y equals f of x from a to b. You took the interval from a to b, divided it into a finite number of subintervals. In each subinterval, you built a rectangle whose height was some point on the curve. You took the area of this rectangle and you added them all up. And that gave you an approximation to the area under the curve. And as you took more and more rectangles, thinner and thinner rectangles, the sum of that finite number of intervals, areas over intervals, converged to what you call the area under the curve. And what worked in one dimension is a very good idea that we can extend to 2 dimensions, or from 2 dimensions, if you like, to 3 dimensions. So over my rectangle, A to B, C to D, suppose I take the interval from A to B, I divide that up into pieces. The interval from C to D, I divide that up into pieces. And so I partition this rectangle into smaller rectangles. And sitting over it is my function z equals f of x, y. I take a point on the surface, and I looked at sort of the parallelepiped. So here is one little rectangle that comes from chopping up the big rectangle into lots of pieces. And here is some point on the surface, let's say it's this high. I compute this parallelepiped. It's like a rectangular box. And this, I know the volume of this. The volume of this, it's a box. What is the volume? It's the area of the base times the height. So this is some little, let's say, the area is, let's say, some delta A sub k. This is like the kth box. And the height is just the value of the function f at some point, x sub k star, y sub k star. So let me just draw a bigger picture to explain what I'm doing. Here's my big rectangle. I divide it up into a lot of little rectangles. Here's one of them. In this little rectangle, I just pick a point. Let's say this is the kth rectangle, xk star, yk star. The height over this point of the function is f of x star, yk star. So this is the height. And I take the area of this rectangle times the height, that's the area of the parallelepiped. And I add that up all over all the pieces. And in advanced calculus, much more advanced calculus, you prove that as the number of pieces goes to infinity, but the area of each base gets smaller and smaller, this sum converges and we get what is the double integral the integral over the region R. I'll write it as f of x, y, dA. A stands for area. This is the limit of a sum, k equals 1 to n. Let's say there are n little rectangles. F of x sub k star, y sub k star, a sub k, as n goes to infinity. So now, to understand this, you can't understand that, I suspect, I hope, but I understand, just from watching what I'm doing. This is something that you have to think about and study about for some extended period of time, which means what you really have to do is sit down in a quiet place with your book and study this. And the pictures in the book are much better than any pictures I can draw. So this is the definition of the double integral of a function over a rectangle. The question is, from the definition, how does one get to a method to actually do the calculation. So we can think of it like this, if you like. Here's my surface z equals f of x, y. And this is my rectangle in the plane. Suppose I want to try to break this up into two pieces, each of which is an ordinary integral. Suppose I take a particular value x, and I look at the line through that fixed value of x in this rectangle. So there's some curve. Let's see if I can use a different color. So I fix an x, and here's a line in the rectangle, and over that, I have a curve. And over this line, the area of this, under this curve, is, I fix x, it's the integral from c to d with respect to y of my function f of x, y. That's that cross-sectional area. And if I move that, if I integrate this, this is a function of x. And if I now integrate this from a to b, that is a way to calculate the area under the surface. And this is one way to understand, or if you like to define, the integral of f of x, y dA over this rectangle R. It is what is called an iterated or repeated integral. So let me give an example of this. Suppose f of x, y is the function 6 minus 2x minus y. If you were to graph this, you would get a plane. When x and y are 0, this is at height 6. When y is 0, this is the line 6 minus 2x. When x is 0, this is the line 6 minus y. I mean, it's hard to draw this thing, but the graph of this function is some plane in three-dimensional space. Again, I really encourage you during these classes to have your book open on your computer and to look at it, because you'll see the pictures much, much, much more clearly. And I want to find the volume under this plane over the rectangle, which goes from 0 to 1 in the x-axis and from 0 to 2 in the y-axis. So here is a rectangle, and over that rectangle is this plane, and I want to find the volume of this prism cut out by this rectangle in the plane. Now, if you fix x, the integral from 0 to 2 with respect, I'm integrating with respect to y goes from 0 to 2. For this rectangle, x is between 0 and 1, y is between 0 and 2. So for each x between 0 and 1, if I integrate, I get the integral of 6 minus 2x minus y dy. So this is the cross-sectional area under this plane when you look along, go from along the line parallel to the y-axis through the point x, through this fixed point x, something like this. And I can do this integral. I'm integrating with respect to x. The integral of 0 to 2, 6 minus 2x minus y dy. So 6 minus 2x is like a constant with respect to y. So this is 6 minus 2x times y, and the integral of minus y is minus a half y squared. And I'm evaluating this from 0 to 2. When x is 2, I get 6 minus 4 is 2y minus a half y squared. And when x is 0, I get 6y minus a half y squared. And when I subtract, I get, when x is, when y is 0, I get 0. When y is 2, I get 6 minus when y is 2, I get 6 minus 2x times 2 minus a half times 2 squared. And when y is 0, I get 0. So this is 2 times 6, 12 minus 4x. 2 squared is 4 over 2 is 2. 12 minus 2 is 10 minus 4x. So here is my problem. I want to compute the double integral over my rectangle R of 6 minus 2x minus y dA. And then my rectangle R is given by x goes from 0 to 1, y goes from 0 to 2. So it's a rectangle in the xy plane that looks like this. That's my R. And I'm going to write this as a double integral. The integral x goes from 0 to 1 with respect to x. And then inside the integral as y goes from 0 to 2, 6 minus 2x minus y dy. So I'm integrating this function first with respect to y, this is the range, and then with respect to x. What is this inside integral? The integral from 0 to 2 of 6 minus 2x minus y dy. X is fixed, x is like a constant. So this is 6 minus 2x times y minus a half y squared from y equals 0 to 2. When y is 2, I get 6 minus 2x times 2 minus a half, 2 squared is 4. When y is 0, these are both 0. So this is 12 minus 4x minus 2. This is 10 minus 4x. That's this integral. So my double integral is the integral from 0 to 1 of this integral. This integral is 10 minus 4x dx. When I integrate 10 minus 4x, I get 10x minus 2x squared, evaluated from 0 to 1. That's 10 minus 2, or 8. So the area of this rectangular prism is equal to 8. So here I had a double integral, and I decided I would integrate first with respect to y and then with respect to 8, and I got an answer, which is 8. You can say, well, suppose I had integrated in the opposite order. Suppose I integrated first with respect to x and then with respect to y. What would happen in that case? Well, let's do the calculation and find out. Again, here's my rectangle. So this double integral over the rectangle, 6 minus 2x minus y dA. If I integrate inside with respect to x first, so x goes from 0 to 1, 6 minus 2x minus y. And then I'm integrating that with respect to y from 0 to 2. So the integral from 0 to 1 of 6 minus 2x minus y dx, let me just write that as just rearrange. This is like 6 minus y minus 2x dx. This is constant with respect to x. The integral of 6 minus y with respect to x is 6 minus y times x. And the integral of minus 2x is minus x squared. And I'm evaluating that from 0 to 1. When x is 0, I get 0. When x is 1, I get 6 minus y minus 1, or 5 minus y. That's what goes inside here. So this double integral over r of 6 minus 2x minus y dA is the integral from 0 to 2 of 5 minus y dy. That's 5y minus a half y squared from 0 to 2. That's 10 minus 2 is 8. And lo and behold, that's exactly what I got when I did the integration in the opposite order. So everything is going right with the world. And we've calculated this double integral. Now, it wasn't just luck that we calculated the problem in two different ways but got the right answer. This is a special case of what is called Fubini's theorem, which says that if f of x, y is continuous on some rectangle R, and you're computing the double integral over R of f of x, y dA, suppose R is x goes from A to B, y goes from C to D. You can integrate, if you like, first with respect to x from A to B, f of x, y dx, and then integrate that with respect to y from C to D. Or you can integrate first with respect to y, and then integrate that from A to B with respect to x. And so long as your function is continuous, you always get the same result. So this is, for us, the most useful fact about double integrals. You can always reduce a double integral to a single integral by this method. Okay. Let's do another example. Suppose we have f of x, y is the function 4 plus 9 x squared y squared. And we take a rectangle R, which is defined by x goes from -1 to +1, and y goes from 0 to 2. So in the xy plane, this is the rectangle, -1, 0, 1, 0, 1, 2. This is my rectangle. And I want to compute the double integral of 4 plus 9 x squared y squared over R. So let me integrate first on the inside with respect to x, the integral from -1 to 1 of 4 plus 9x squared y squared dx. And then I'm going to take that and integrate that. Y goes from 0 to 2 dy. So what is that? When I integrate 4 plus 9x squared y squared with respect to x, I get 4x, and the integral of x squared is the third x cubed. 9 over a third is 3, plus 3x cubed y squared, evaluated from x equals -1 to x equal +1 dy. When x is 1, I get 4. So this is, let me just write this out. This is the integral from 0 to 2. When x is 1, I get 4 plus 3y squared. And when x is -1, I get -4. -1 cubed is -1, minus 3y squared dy. This is the integral from 0 to 2. 4 minus -4 is 8. 3y squared plus 3y squared is 6y squared dy. This is 8y plus the integral of y squared is y cubed over 3 plus 2y cubed, evaluated from 0 to 2. When y is 2, I get 2 times 8 times 2 is 16. 2 times 8 is 16. I get 32. And when y is 0, this is 0. So the answer is 32. So I encourage you to, if you're not looking at your book, you can open your book on your computer screen at the same time that you're on Zoom and take a look at the pictures of what's going on here and how the calculation is done and what it means. That really is very useful. Are there any questions about this?
Excuse me, Professor, I have a question about the exam that's on my math lab today. Like, I know you said that we didn't have to do it today, right? So does that mean that we're gonna do it like next week? Like you're gonna
I'm going
schedule
to
it?
take a look at it tonight and see, because I mean yeah, I'll take a look at it tonight and I'll post an announcement on Blackboard tonight about that exam.
Okay, thank you, Professor.
Okay. Mm.
So we're not supposed to take it today, right?
You don't have to take it today. I mean, from my point of view, these online exams are not very much different from homeworks, but in any case, no, you do not have to take it today.
I just want to make sure.
Yeah, no, don't worry about that. Okay. Let's just recall one other analogy with functions of one variable. If you have a function y equals f of x on the interval from a to b, what we defined as the average value of f is the integral of the function from a to b divided by the length of the interval. That was the average of f of x on an interval from a to b. If we have z equal to a function f of x, y on a rectangle R given by, so this is x is between a and b, but for our rectangle, we have, let's say, x between a and b, y between c and d. We want to say the average value of this function f on the rectangle. It's the integral over the rectangle divided by the area of the rectangle, which is, of course, for a rectangle A, B, C, D, the area is the base B minus A times the height. That's the area of the rectangle. But in general, because we don't have to integrate necessarily over rectangles, if you want to find the average value of a function of two variables over a region R, you integrate over R and divide by the area of R. So this is just a definition which we note, because, okay. Let me do one or two problems from the end of this section, just so you see more examples of what's going on. So this is section 16.1, exercises. So problem number 7 is you're given an iterated integral. It's a double integral, 4xy dy dx, 0 to 0, 1. So this means you have this function, you have the function 4xy, you're integrating with respect to y from 0 to 1, and then integrating that from 0 to 2 with respect to x. So what is this inside integral? The integral from 0 to 1 of 4xy dy, x is a constant. The integral of 4y is 2y squared. So we're integrating that from y equals 0 to 1. When y is 1, you get 2x, and when y is 0, you get 0. So this integral is equal to 2x. So you plug that in here, we get the integral from 0 to 2 of 2x dx. Integral of 2x is x squared from 0 to 2, and the answer we get is 4. Let's take another example. This one, should I take one a little bit more challenging? Suppose we have the double integral over R of x over 1 plus x times y, where the rectangle R is given by all the points where x is between 0 and 1, and y is between 0 and 1. That's the rectangle. It's the unit square. So we have to decide, should we integrate with respect to x first or with respect to y first? And I don't know. Sometimes you just have to experiment and see what happens. So let's say I integrate first with respect to y. So x over 1 plus xy dy, y goes from 0 to 1. And then I'm going to integrate that from 0 to 1 with respect to x. So what is this inside integral? This is the integral from 0 to 1, x over 1 plus xy dy. X is fixed, so I can take that outside the integral sign. That's x times the integral from 0 to 1, 1 over 1 plus xy dy. What's the integral of 1 over 1 plus xy with respect to y? That is, if I take the log of 1 plus xy, log of 1 plus xy, if I differentiate that with respect to y, I get x over 1 plus xy. actually. So in fact, this integral is the log, let me just write, this is the log of 1 plus xy. Because if I differentiate this with respect to y, I get x times the derivative of 1 over 1 plus xy. And I'm evaluating that from 0 to 1, from y equals 0 to 1. When y is equal to 1, I get the log of 1 plus x. And when y is equal to 0, I get log 1, which is 0. So this inside integral is just the log of 1 plus x. So this is the integral from 0 to 1 of the log of 1 plus x dx. Now, one of the unfortunate things of vector calculus is you have to know calculus. So how can we integrate this? Well, let's see. There's several ways. Suppose I change variables. Suppose I let u equal 1 plus x. So as x goes from 0 to 1, u goes from 1 to 2. Log of 1 plus x is log u du. So this is, what's the integral of log u? U log u minus u. You can do that by parse, or you can remember it from Calc 1, from 1 to 2. So this is, when u is equal to 2, 2 log 2 minus 2 minus 1 log 1 minus 1. Log 1 is 0. So this is equal to 2 log 2 plus 1. So that is what I got. Let me just review that again, because it's always good to see things twice. It was number 28. The integral over the rectangle of x over 1 plus xy dA. If I integrate that, and this is x is between 0 and 1, and y is between 0 and 1. So if I integrate with respect to x from 0 to 1, and then I integrate that with respect to y from 0 to 1. Sorry, I want to integrate with respect to y and then with respect to x. The integral of x over 1 plus xy dy, if I make a change of variables that say v equal 1 plus xy, so dv is x dy, this becomes the integral of dv over v, which is log of v. And if I'm integrating as y goes from 0 to 1, then v goes from 1, y equals 0 to 1 plus x. So this is the log of 1 plus x. So this is the integral from 0 to 1 of the log of 1 plus x dx. And in this, if I let u equal 1 plus x, this is the integral from 1 to 2 of log u du, which is u log u minus u from 1 to 2, which is 2 log 2 minus 2 plus 1 is minus 1. Yeah, minus 1. Now, here you have to notice I integrated first with respect to y, then with respect to x. That was just a choice. Suppose I did it in the opposite order. So suppose I integrate on the inside x over 1 plus xy dx from 0 to 1. And then I take that and I integrate that with respect to y from 0 to 1. So that is actually, I think, a lot harder. So what is the integral of x over 1 plus xy dx? I guess it might be possible to do that, but it might be a little bit trickier. Let's see. Let me see if I can figure out a way to do that. Not necessarily the best way, but let's see. I'm integrating x over 1 plus xy. So let me write that as 1 over y times xy over 1 plus xy, which I'm going to write as 1 over y, 1 plus xy minus 1 over 1 plus xy. That's equal to 1 over y minus 1 over x, 1 over 1 plus xy. So I think, even though this looks weird, that this is a correct algebraic statement. See, 1 over y, xy. 1 plus xy minus 1, 1 over y, minus 1 over y, 1 plus xy. And then I'm integrating x over 1 plus xy dx. So that's the integral of 1 over y minus 1 over y, 1 over 1 plus xy dx. This is x over y minus 1 over y. And the integral of 1 over 1 plus xy with respect to x is the log of 1 plus xy. If I differentiate just that, minus the log of 1 plus xy. If I differentiate this with respect to x, I get 1 over y squared. I differentiate this with respect to x, I get 1 over 1 plus xy times y. And I'm integrating this with respect to x from 0 to 1. So when x is equal to 1, I get 1 over y minus the log of 1 plus y. And when x is equal to 0, I get 0 minus 0. I just get this. So then if I integrate from 0 to 1, 1 over y minus the log of 1 plus y dy. This looks like this. The integral of 1 over y is log y minus 1 plus y log of 1 plus y minus 1 plus y. Let's see. If I differentiate this with respect to y, I get 1 over y. I get log of 1 plus y, 1 plus y over 1 plus y. Yeah, that's correct. And I'm evaluating this from y equals 0 to 1. Well, it's not going to work. The lesson from this is, in principle, you can choose either one of two ways to do an iterated integral, but in many cases, one way will work easily, and the other way will be too hard to solve or much too complicated. And how do you decide which order to integrate with respect to? First x or first y? The answer is sometimes you try one. If it works, good. And if it doesn't work, try the other. Right? That's the lesson of all this. So here's another example. And in fact, in this example, we're coached because the book tells us that in one order, the problem is going to be hard to do, and on a different order, the problem is easy to do. This is number 40. We take the rectangle R to be the rectangle where X goes from 0 to 1, and so this is X, and Y goes from 0 to pi over 3. And we want the double integral over R of Y cosine xy dA. So which way should we do first? I have no idea. I'll just try one, then I'll try the other. So let's say first we differentiate with respect to X, Y cosine xy dx from 0 to 1. And then we integrate that from Y going to 0, from 0 to pi over 3 dy. So what is this integral? The integral of Y cosine xy dx is equal to the sine of xy. Because if you differentiate x sine of xy with respect to x, you get y cosine xy. And integrating this from 0 to 1, x going from 0 to 1, when x is 1, this is sine y, and when x is 0, this is 0. So this is just sine 0. So we're integrating from 0 to pi over 3 sine of y dy. So the integral of the sine is minus the cosine from 0 to pi over 3. So this is minus the cosine of pi over 3 plus the cosine of 0, or 1 minus, and the cosine of pi over 3 is a half. So we get the answer a half. Let's say I pick the other way to do it. Suppose I say that this double integral I want to integrate first with respect to y, and then with respect to x. So what is the integral with respect to y of y cosine xy dy? I guess we can try to integrate by parts. If we have this is y, and this is cosine xy, the derivative of y with respect to y is 1. The integral of cosine xy with respect to y is sine xy, 1 over x sine of xy. So this is equal to y over x sine of xy. But now we already have a problem because we'd be dividing by x, and this is just not going to work. So this is way too complicated, maybe not even defined. So in this case, there was one way which gives us an answer easily, and the second way does not. Okay, so what we've just been discussing is integration over a rectangle. But suppose we have a more general region. So here's a typical example. Suppose we have a region R defined as follows. X runs from A to B, and we have two functions. We might have a function y equals g of x, and another function y equals h of x, and g of x is less than or equal to h of x for all x between A and B. So we can look at the region which is bounded above by one curve bounded below by another, and by the vertical lines, x equal a and x equal b. So that's my region R. And we can ask about the double integral over R of a function of two variables. And in this case, there's something which is sort of, in some sense, natural about what to do. For each x, integrate from the bottom to the top along this vertical line, from g of x to h of x, f of x, y, dy, and then integrate that as x goes from a to b. And that's an iterated integral of a function over a region which is not a rectangle, but which is bounded by two lines parallel to the y-axis and by functions g of x and h of x. So let's look at an example. Suppose we have two parabolas. We have the parabola y equal 3x squared. And we have the parabola, so this is some function g of x. We have the parabola h of x equal to 16 minus x squared. What does this look like? So 16 minus x squared that parabola looks like this. This is the vertex. It's opening down. Looks like that. The parabola 3x squared, when x is 0, it's 0. When x is 1, it's 3. When x is 2, it's 12. When x is 3, it's 27. So parabola looks sort of like this. And there's a region that's between the two parabolas, that's bounded by the parabolas. It's this region here. So this is a region. How do we describe that region? It's bounded below by this curve. Oops. Sorry. It's bounded in this area. It's bounded above by the curve 16 minus x squared. And it's bounded below by 3x squared. And where do these two curves intersect? They intersect when g of x equals h of x. That is, when 3x squared equals 16 minus x squared. That's the same as 4x squared equals 16. X squared equals 4, x equal plus or minus 2. So when x is equal to 2, this is 12. They're both 12. And this point is minus 2, 12. So this region R can be described as follows. X goes from minus 2 to plus 2. And y in this region is bounded above by 16 minus x squared and bounded below by 3x squared. So that is our region R. And let's say we have a certain function that we want to integrate over this region. So the problem is to integrate the function f of x, y equal to 2x squared y over this region R. So we're going, of course, because that's our only technique, we're going to set this up as a double integral. How do we do that? Well, we follow the recipe that we're given in this formula. So the bottom is the function 3x squared. The top is the function 16 minus x squared. So over this region, oops, the double integral over R of 2x squared y is an integral with respect to x. X goes from -2 to +2. And then an integral with respect to y from g of x up to h of x of the function 2x squared y. Now, the integral of 2x squared y dy, the indefinite integral, is just x squared y squared. If you differentiate this with respect to y, you get 2x squared y. So this is the integral from -2 to 2, the integral from g of x, 3x squared, up to h of x, 16 minus x squared y squared, dy, integrate that with respect to x. So what is this inside integral? Sorry, this was the integral of 2x squared y dy, and I just calculated that. This is the integral from -2 to 2 with respect to x. What do we have here? We have x squared y squared evaluated from y equal 3x squared to y equals 16 minus x squared. Let me just do this calculation. So the integral of 3x squared, 16 minus y squared, 2x squared y dy, is x squared y squared, evaluated from y equal 3x squared to y equals 16 minus x squared. So this is equal to x squared, 16 minus x squared squared, minus x squared, 3x squared squared. So now we have to do a little bit of algebra. What is this? This is x squared. When we square this, 16 squared is 256 minus 32 x squared plus x to the 4th minus 3 times 3 is 9. X squared squared is x to the 4th times x squared is x to the 6th. X squared, 16 minus x squared. 256 minus 32x squared plus x to the 4th minus 9x to the 6th. This is equal to 256x squared minus 32x to the 4th plus x to the 6th minus 9x to the 6th minus 8x to the 6th. That's what this inside integral is. And then we plug that in here. So we get the integral from -2 to 2. Plug this in. Now we integrate. We get 256 over 3x cubed minus 32 over 5x to the 5th minus 8 over 7x to the 7th, evaluated from -2 to +2. So you do your arithmetic and you get your answer. That is the story. So we're doing double integrals, and we're doing them by reducing them to iterated single integrals. And this works well, of course, only if you can do the ordinary integral. And that's why Calc 1 and Calc 2 are prerequisites for vector calculus, I guess. Okay, so what we talked about today are the first two sections of chapter 16, which is simply learning what is the double integral and how to calculate it. And we'll talk about this a little bit more on Monday, I guess, of next week. And then there's a week break for Thanksgiving, and we're back the following Monday. Okay. Any questions about any of this? There's a lot to learn in this course, and we've done differentiation. Now we're doing integration, and our goal in some sense is to figure out something like the analog of the fundamental theorem of calculus, which you learned in first semester calculus for functions of one variable. And we want to figure out what it means when we're dealing with functions of 2 or 3 variables, especially functions of 2 variables for us. And the more time you can spend studying chapter 16 and 17, the much better off you will be about learning this material. Okay. Okay. That's it for today. Enjoy the day. A little bit chilly.
Professor,
Yes.
when are you gonna post the grades for the exam that we had?
I'm going to try and get them posted by tonight if I can. I've been actually I've been sick in bed for most of the last 2 weeks, and just with the flu, so, and getting up just to teach my classes there, but I'm going to try and finish them today and post them tonight.
Okay, I understand. Thank you.
Okay. All right. Bye all.